In this video, we will focus on what an electrolytic cell is. So already in this chapter, we've learned about a battery, and we know that it goes by several names. We could call it, in addition to saying it's a battery, you also might call it a galvanic cell or a voltaic cell. And no matter what you call it, it uses a redox reaction that's spontaneous. So in other words, it has a positive E cell and it generates a current. So a battery is always going to be set up so that the whole purpose is that you have a spontaneous reaction that's going to move electrons around. An electrolytic cell is basically the opposite of a battery. It's where you have a reaction that you want to run, but it's a not spontaneous reaction, so you use electricity to force that reaction to go in the non-spontaneous direction. So if I tell you something is a galvanic cell, or a voltaic cell, I'm telling you E cell is positive. If, on the other hand, we're talking about something that's an electrolytic cell where we're using electricity, electric current to drive the reaction, that means that the E cell, the cell potential, is going to be negative. So one of my personal favorite reactions is this reaction here. This is aluminum oxide, or alumina, being broken down into pure aluminum metal and oxygen. This is not a spontaneous reaction, it's one that has a negative E cell. So the way that aluminum metal is made is we take this alumina out of the ground, it's actually a white powder, and run very, very high amounts of electric current through it to change it into aluminum metal. And it's one of my favorite reactions because for 2 summers I worked at Alcoa during my time in college, and this is actually me while I was in college standing on top of a huge electrolytic cell. They call them pots, or a pot line, and this is a rod of copper, and on the end of it is a carbon anode, and the electricity comes in, goes down through the copper rod into the anode that's down in here, and there's just a molten bath that contains this aluminum oxide and makes it into aluminum. Then something comes along, opens this door at the end, and actually, it looks like an elephant trunk almost, and suctions molten aluminum metal out of the bottom of this pot. Very, very hot. I'm standing there in the middle of summer with like thick cotton pants and thick cotton shirt, but it's like hundreds of degrees up there. Very, very, very warm. But a job that was also very interesting. So that's me on a real life electrolytic cell. So here we've got diagrams comparing a voltaic cell to an electrolytic cell using the same anode and cathode. So here we've got zinc, that's our anode. The electrons are leaving. They're going through a voltmeter that's showing, hey, there's some electric current being generated here, and the electrons go to the cathode. The electrolytic cell is really the opposite. They've got a voltage source here that's forcing the reaction to go in reverse. So copper now is losing the electrons. The electrons are coming over here to what is now the cathode, which is zinc. So everything's really going in the reverse of what it was before. As we talked about when we first discussed batteries a few days ago, this is also the premise on which rechargeable batteries work. If a reaction that's spontaneous has completely gotten to equilibrium, you can reverse that reaction by applying an electric current, and that's what an electrolytic cell does. Again, with the compare and contrast here, I want you to notice on a voltaic cell, the anode is the source of electrons. That's where they're coming from, that's where they're leaving. And the cathode is pulling in electrons to itself. So it's pulling the electrons in this way. On an electrolytic cell, the anode, you might think of it more as it's the place where electrons are being pulled away. So notice in the electrolytic cell now the copper electrode is our anode, and electrons are leaving here, and they're not so much going on their own accord as they're being pulled away by the voltage source. The cathode now is the zinc, so we've got this reaction going in reverse, and the electrons are entering, or they're being forced into the cathode. It's also worth noting that as the electrons leave the anode mass is going to decrease as the copper goes from solid copper into aqueous copper, and the zinc, here the mass is going to increase because we're bringing in electrons, so zinc is going from zinc 2 plus aqueous into solid zinc. And this is another interesting thing I noticed while working at Alcoa. The anodes in the electrolytic cell, they would get consumed as time goes on, and so every so often, every 14 days I think it was, a crane would come along and it would replace all the anodes, or a section of the anodes in each cell, so that you never run out of anode completely. When we're talking about electrolytic cells, it's often interesting and of interest to talk about how much time it takes to, for example, generate a certain amount of metal. So like in that aluminum electrolytic cell, how much aluminum do you make in 24 hours? And a lot of these calculations end up really being an application of factor label method, using some important facts here, which are on your AP chemistry reference sheet. 1 ampere, or 1 amp of current, is defined as 1 coulomb moving through the wire every second. And also 96,485 coulombs are equal to 1 mole worth of electrons. That's the charge of 1 mole of electrons. So in this problem we say silver can be plated out of a solution, so containing silver ions, and plated out means it goes from being silver in solution to silver maybe coating something. According to the half reaction, Ag plus 1 electron makes solid silver. How much time in minutes does it take to plate 12 grams of silver using a current of 3 amperes? So we want 12 grams of silver. And I see here I can relate grams to current to charge using moles. So if I go from grams, there's 107 grams of silver in 1 mole of silver. And then this is an important step. For silver, it's pretty simple. 1 mole of silver, we're going to see 1 mole of electrons transferred because of this right here. But if we were dealing with like zinc or copper on the previous page, then we'd be transferring 2 moles of electrons. So this step is not so important on this problem because every silver is just gaining 1 electron. But if we have something that's gaining 2 or 3 electrons, you want to make sure you pay attention to that in your calculation. So now we've got moles of electrons. We can use this fact here to say that for every 1 mole of electrons, that's 96,485 coulombs. So again, just to touch base on what we were trying to figure out, we've gone from grams to moles, and from moles of silver to moles of electrons, and now we're figuring out how much, we know at this point how much charge we need to plate out 12 grams of aluminum. We want to go from charge to time. Well, we have a current of 3 amps, and 3 amps basically is 3 coulombs every second. So if there are 3 coulombs in 1 second, they want time in minutes, there's 60 seconds in 1 minute. That will finally get us to minutes, which is the amount that we want. So I'm going to pause and calculate this. I found after doing all the multiplication and division in this factor label method that it will take 60 minutes to plate 12 grams of silver. So if we were in for 120 minutes, then this process would plate 24 grams of silver. All right, in this problem, it says we've got some molten magnesium chloride, and we are applying a current to it for 18 hours, and we're obtaining this many grams of chlorine gas. And it says, what is the value of the current in amperes? So if I'm looking for current in amperes, we need an answer that has coulombs over seconds. We need to put some time in the denominator, which 18 hours. And we need a ratio for our answer. So we need something we can convert to coulombs in the top. And we have 4.8 times 10 to the 5th grams in the top, grams of Cl2 in the top. And we can, basically we're going to be able to go from grams to moles, and once we know moles, we can get moles of electrons, and moles of electrons will allow us to relate to coulombs. So that's exactly what I'm going to do. I'm going to do with the grams part of the problem first. There are 70 grams of chlorine in 1 mole of Cl2. Now here's the step where I said on the last problem it didn't seem that critical, but here it's going to matter more, where we're thinking about how many electrons are transferred for every mole of the substance that we're forming. So if we think about this process in MgCl2, we've got 2 chlorine ions in this molten solution, and we're changing them into chlorine gas. And so that means in that process 2 electrons are being lost. So for every 1 mole of Cl2 that's formed, this is going to involve a transfer of 2 electrons. So this step is a little bit more critical in this problem than it was in the previous one. But don't ever forget to think about, in this chemical that I'm forming, how many moles of electrons are transferred. So for 1 mole of electrons, there are 96,485 coulombs. And so, I've got the unit that I've been looking for on the top. I want coulombs in my numerator because I'm trying to get a unit of amperes, which is coulombs in the numerator. Now it's time to work on the denominator. I started with units of hours. I want to go from hours to seconds. So I'm going to do 1 hour is 3,600 seconds. So that'll get me to the unit of seconds that I want in my answer. So again, I'm going to have to do a bunch of multiplication and division. And when I do that, I got 20,420 coulombs per second, which is the same thing if I take into account sig figs, which would be 2, and have 2.0 times 10 to the 4th amps. That's the amount of current, which is a pretty big amount of current. That's the amount of current it would take to generate, well, I had a pretty big amount of chlorine, 48,000 grams of chlorine gas over a period of 18 hours.